Good afternoon and welcome to the session number 3 from the playlist of dual nature of radiation and matter. The topic is the energy and the momentum of photon, and based on this topic I have written here 4 important points which will help us to understand this topic in brief. This session is in continuation of the session number 2. So the first point here is that from the Einstein's mass energy relation, E is equal to h into F, where F is the frequency of the incident radiation, and from the Einstein equation, that is the energy of the photon can also be written as mc square. So from this relation, that is E is equal to hf is equal to mc square, I will be getting the mass of the photon, or you can see the kinetic mass of the photon, which is the other name of it, equal to hf upon c square. Now if I substitute the value of f equal to c upon lambda, here c is the velocity of the light in vacuum and lambda is the wavelength of the incident radiation. So if I substitute the value of f, which is equal to c upon lambda, then I will be getting another equation which is equal to h upon c lambda. So the mass of the photon is equal to hf upon c square in terms of the frequency of the incident radiation, and it is also equal to h upon c lambda in terms of its wavelength. So the mass of the photon can be calculated by this formula if the wavelength of it is known, and the mass of the photon can be calculated by using this relation, that is hf upon c square, if the frequency of the incident radiation is known to us. The second important point is the momentum of the photon. So the momentum of the photon will be equal to the mass of the photon, or you can say the kinetic mass of the photon multiplied by the velocity of the photon. So this will be equal to hf upon c square into c. Finally, I will be getting the value as hf upon c, and if I substitute the value of f as c upon lambda, then I will be getting another equation, that is h upon lambda. So here I have written that the mass of the photon has got two important formulas, that is hf upon c and h upon lambda. So hf upon c is the momentum of the photon in terms of its frequency, and h upon lambda is the momentum of the photon in terms of its wavelength. Now the third important point is the de Broglie relation. So in 1942, de Broglie, his name is Louis de Broglie. So in 1942, Louis de Broglie asserted that like the light, mass also has got a dual behavior. That is, there is a wave associated with a moving particle which is called the matter wave or the de Broglie wave. And so here from this equation, that is the Einstein mass energy relation, and the Einstein equation, that is E is equal to mc square, I am getting the wavelength of the photon as h upon mc. Now here what I have done is I have substituted the value of f as c upon lambda, and then by equating these two equations, from these two equations I am getting the value of lambda as h upon m into c. Now this equation is also applicable to the moving particles. That is, the wavelength of the wave which is associated with a moving particle is equal to h upon m into v, where v is the velocity of the moving particle and m is the mass of it. So the wavelength of the wave which is associated with a moving particle is equal to h upon mv, and this is also equal to h upon p, where p is the momentum of that particle. And in terms of the kinetic energy, this can be written as h upon under root 2me. We know that kinetic energy is equal to, let us say kinetic energy E is equal to half mv square. So if I multiply this equation on both sides by m, so this will be equal to 1 by 2 m square v square. So from here this will be equal to mv square upon 2. So from here the value of mv will be equal to under root of 2me. So this is what I have written here. So the wavelength of the wave which is associated with the moving particle, which is also called the matter wave or the de Broglie wave, is given by the relation, that is lambda will be equal to h upon m into v, and this will be equal to h upon p, where p is the momentum of it, momentum of the moving particle, and this is equal to h upon under root 2m into E, where E is the kinetic energy of that moving particle. And the wavelength of the photon will be equal to h upon m into C, where C is the velocity of light in vacuum. For a charged particle, this wavelength will be equal to h upon p. This will be equal to h upon under root 2me, and now this is also equal to h upon under root 2mq into v, where q is the charge on that particle and v here is the potential difference through which that particle is accelerated. So for a charged particle, these are the three important relations, that is h is equal to lambda is equal to h upon p. This is equal to h upon under root 2me, and if the charge on the particle is known to us and the potential difference through which it is accelerated is known to us, then we can also find the wavelength of that charged particle. So thank you very much for joining this session. In the next session, I will be coming up with a question which will be based on the photoelectric effect. So till then, have a nice day. Bye.